Hope screen is visible to all.
Yes, sir.
Okay.
Yes, sir.
So in today's session, we discuss about model number 4, that is embedded system design concepts. In the previous session, we have completed model number 3, and regarding that week assignment work is given to you in the Google Classroom. So submit that one before due date. So I have extended that one to second assignment is up to Saturday. So in this model number 4, once again it is a theoretical concept about embedded system with a little bit introduction of some modules. So let us discuss about what are the things we are going to study in this module are the characteristics of embedded system, the quality attributes of embedded system. In quality attributes, we have operational and non-operational quality attributes. Then we have the design of embedded system application and domain specific concepts. Meanwhile, the hardware software co-design. Then we have program embedded firmware design and development. So here once again you are introduced with the design of embedded system. In the previous model, we discussed about what is the embedded system. Now we start designing of that one using these concepts. So here, let us begin with the first concept. It is the characteristics of an embedded system. So the embedded system, it has characteristic, that is the application and the domain specific, the reactive and real time, the operation. It operates in harsh environments. The distributed system it must be, and it should have small size and small weight, and it should have some characteristics regarding power, the power concerns. So what are these 6 characteristics of an embedded system? So here, as we have the characteristic indicates, it must be a application and domain specific. So each embedded system is having certain functions to perform, and they are developed in such a manner to do the intended functions only. So as we know the definition of this embedded system, it is designed to perform a specific task. So the characteristics of this embedded system is what? It must be a application specific or domain specific. So it is intended to do a specific function only. So they cannot be used for any other purpose. Obviously, when it is a specific design for specific function or a task, obviously it should not perform any other task. So it is the major criteria which distinguishes an embedded system from the general purpose system. As we went through the differences between embedded system and the general purpose system, obviously this is the specification, the uniqueness of this embedded system is what? It is designed for a particular task. Example, the embedded control units of microwave oven or the air conditioner are specifically designed to perform certain specific tasks. They won't do other tasks except it is designed for. So this one is the characteristics of an embedded system. That is, obviously it appears in the difference of general purpose and embedded system, as well as it is the one of the characteristics. Then it comes to reactive and real time. Obviously, it must be a reactive one. For any changes at the input, the output must change. It must be reactive. It should react for the inputs. Then it must react in real-time fashion. That means embedded system produces changes in output in response to the changes in the input. That is called reactive. So they are generally referred as reactive systems. Real-time system operation means the timing behavior of the system should be deterministic. Means the system should respond to a request or a task in a known amount of time. So within the given time or the known time, the system has to perform its task. That is nothing but it must be a reactive one, so that whatever the changes in the input, those things will be calculated, processed by changing the states or the physical condition of the outputs. Okay, so that is the reactive and real-time characteristic. Example we are going to find the reactive and real-time. Obviously, it is about mobile phone if you consider. So the embedded system, which is nothing but the mobile phone, whatever may be the input, the touch screen, what we are going to use nowadays in all the mobile phones, once you touch the screen, the respective task will be done within the known time. If there is a delay, obviously we are not going to consider that one as a real-time embedded system. Okay. So example they are going to provide it is a flight control system. So whatever the embedded system we are going to design for a flight, so the controlling units must be a real time. Then comes in the car. So nowadays the cars are featured with the anti-lock braking system. Anti-lock braking system, ABS we are going to say. So this ABS system is nothing but a real-time one. Then if we go for the third characteristic, it is operates in harsh environment. So obviously, whatever the embedded system means, what the system I have adopted, that is nothing but the headphone. Okay, the Bluetooth enabled wireless headset. It must be. It is a part of the embedded system. So once we come across that characteristic, the part that is nothing but distributed. So here, whatever the system, the environment, surrounding environment, if it is a harsh one, obviously it should be operated in that environment. So the design should take care of the operating conditions of the area where the system is going to be implemented. For an example, if the system needs to be deployed in a high temperature zone, then all the components used in the system should be of high temperature grade. So here we are talking about the design of embedded system. Now we know the knowledge of what is this embedded system. Now we started designing that embedded system. Nothing but let me say, I have planned to design a washing machine. So once we, how to design that washing machine? If I go for the characteristics or the environment, it is a high temperature zone. So in the high temperature zone, whatever the components, equipments, what we are going to use to design that, to create that washing machine in the high temperature zone, those components withstand that temperature. Okay, beginning from the small part, that is a nut or screw, up to its panel. Okay, the panel, it may be metal or non-metal, or it is a fiber, or it is a something else. So all those components must withstand that high temperature conditions. So example, it is not only this high temperature, there are so many harsh environments what we are going to observe. It is corrosion. It may happen to any component, any part of the component. Corrosion, it should be outcome from this corrosion. Then the power supply fluctuations. Obviously, in the villages we are going to observe there is a power supply fluctuations. So whatever the component we are going to design, and it will be kept in that environment. So the component should withstand that condition, harsh environment. That is power supply fluctuations, corrosion, and component aging means the age of the component will be long durable one, and other factors that need to be taken care into consideration for embedded system to work in a harsh environment. And the fourth characteristics, as I said, it is a distributed one. So the term distributed means that embedded system may be a part of a large system. So it must be a distributed one. It is not like that the system, only one system is designed and it is performing all the tasks, whatever it is designed for. It is not like that. So it must be a distributed one. So many number of such distributed embedded systems form a single large embedded control unit. So embedded system, it may be a part of the large embedded system or embedded control unit. So it must be distributed. Example, we may say it is the automatic teller machine, that is ATM machine, what we are going to use for transaction purpose, currency transaction purpose. So here the ATM contains the small embedded systems which are connected or which are part of a single large embedded unit. Let me say the ATM machine is a single large embedded control unit, a huge unit. So how to design that huge unit? By considering a small embedded systems which are connected together to make one large embedded unit. So the ATM machine is the example. So what are the small parts, the distributed embedded systems, what we are going to observe in that example, it is the card reader. The first equipment where we are going to insert our card for currency transactions. So it is card reader. It is a small embedded system which is incorporated in the ATM large machine, responsible for reading the card and validating the user card. Okay, then once it is designed, that particular embedded system is designed for the two tasks. It is reading the card and validating whether the card is authenticated or not, or a valid card or not. Then the transaction unit for performing transactions where the currency is going to be dispatched. Okay, that is the transaction unit performing. Okay, then currency counter for dispatching and vending currency. So the currency counter is it is a small part of the distributed embedded system which is responsible for the dispatching the currency. Okay, then the transaction is nothing but this the transaction between the ATM machine to the main branch or the server, so that the transaction has to be happening through electronic media. So small embedded system, that is transaction unit. Then printer. Obviously, after the transaction, we need some printing materials, the printout, the details of the transaction in the printed format. So a small printer, obviously, printer is a embedded system. So it is a part of that embedded system, the large embedded system, let me say. So large embedded system is having, or it is the connection of small embedded system. Those small embedded systems are considered as the distributed embedded systems. So the embedded system must be the characteristics of a distributed fashion. Then obviously nowadays any device what we are going to operate with, the expectation of the user, it is what? It must be a small size and less weight. So the product parameters or aesthetics are like size, weight, shape, style, and other conditions or requirements of the user will be one of the deciding factors to choose a product. So moreover, it is convenient to handle a compact device than a bulky one. So in embedded domain, the compactness is a significant deciding factor. So most of the application demands So as we say, the application or nothing but the requirement of the user, it is a small sized and low weight products. Obviously, the size regarding the mobile phone device, obviously, we are thinking about it must be small size and less weight. But it is not applicable for all the embedded system. Obviously, if we are thinking about to design a car, obviously we are thinking about not about the size of the car, small size. Obviously, we need 4 plus 1, 3 plus 1, 2 plus 1 based on the number of seats must be added in that design of that car. So, and what about weight? Obviously, regarding the car, we need the less weight. So we need what? The more number of passengers should be used, more number of seats will be allocated in that car, but the weight of that car must be a lower weight. So here there is a adjustment is there with respect to size and weight, but most of the products are requiring small size and less weight. Then the last characteristics of this embedded system is the power concerns. So obviously we need the power used by this system, it must be less. Less power, more performance. That is the demand of the embedded system users. So embedded system should be designed in such a way as to minimize the heat dissipation by the system. So the production of high amount of heat demands cooling requirements like cooling fans, which in turn occupies additional space. Obviously, if you go for the laptop or a desktop or the CPU or any embedded system, in the power control box, the power box is going to have a small cooling fan, because whatever the heat is dissipated, it will be removed by using these cooling fans. So which in terms occupies additional space. So we need what? The heat must be less, so that whatever the extra components what we are using to control that characteristic or behavior, so that will be reduced. So additional space will be taken by these cooling fans and make the system bulky. So what we are designing here. So we are going to use a chip and it is going to produce a heat. So to remove that heat, to make that chip cool, we are going to use the fans. Nothing but to take one work, we are taking the help of some more components. Obviously, they are going to create a bulky design. So select the design according to the low power components like low dropout regulators and controllers or a processor with power saving modes. So these are the characteristics what we are going to observe with respect to an embedded system. Then we go for the quality attributes, operational and non-operational. So here the various quality attributes that needs to be addressed in any embedded system development are classified into operational quality attribute and non-operational quality attribute. So what is this operational quality attribute? So when the system is working, when it is in the on mode, when it is in the on mode, or it is in the online mode, or it is in the operational mode, the attributes related to the embedded system when it is in the operational mode or in the online mode or it is operating. So at that time, the attributes what we are going to prefer, those are listed as response, the throughput, security, safety, reliability, and maintainability. So these are the few operational quality attributes what we are observing in the design of embedded system. What is this response? The response is a measure of quickness of the system. Obviously, it is dependent on the characteristics like real time and reactive. It gives us an idea about how fast the system is tracking the changes in the input variables. most of the embedded system demands fast response, which should be almost real time. Obviously, this attribute, this behavior of an embedded system, when it is working, when we consider that that attribute, obviously it is related to the characteristics of that embedded system, that is real time. It must be real time, so that the tracking must happen, the changes in the input side. Based on that changes in the input side, they will be measured, the quickness of the response. For an example, the embedded system deployed in flight, as we discussed in the real-time characteristics, obviously, the example is the flight control application should respond in real-time manner. It is not like that all embedded system must support this characteristic, that is real time. Okay, response must be there, but it may be real time, it may not be. For an example, if I go for a toy, okay, where we are not expecting the real time operations. Okay, the response may be delayed, but we are not concentrating while designing that toy. We are not concentrating on the real time concepts. Okay, if you go for the remote car toy, even we operate some inputs in the remote, the car should not respond immediately. There is nothing but what? Not non-real time embedded system. So real time is the option there, but the user demands it must be a real time. Okay, so keep it in mind. All embedded systems are not characterized as real time embedded systems. Keep it in mind, because we have varieties of operations like the ATM machine, the transaction, what we are going to observe, but it is up to real time. We are not expecting this must be a real time only. If I go for the call, once I dial a call using the embedded system, that is mobile phone, whatever the communication is there, but our expectation is real time, but it is not happening. Okay, means we are not concentrating in that real time, but the expectation must be there. The response, then the throughput. The throughput deals with the efficiency of a system. So how much it is efficient. In general, it can be defined as the rate of production or the operation of a defined process over a stated period of time. So it is the rate of production, the throughput. So in the given time, or the efficiency based on the throughput, nothing but how much output we are expecting. So whether the output is coming or not, it is achieved by the embedded system or not. Okay, so once we design an embedded system, like for communication media, it is a mobile phone. Let me take the example of that throughput. Throughput, nothing but the efficiency. Once I click the dialer button, so what is the throughput? How it is efficient that it is going to connect that end user, okay, destination within the specified time, or process over the stated period of time. So this is measured in terms of benchmark. So we're going to say benchmark. So it is going to say once I dial, the connection between two mobile phones, sender and a receiver, the two mobile phones, it is going to occur with a span of time. Let me say it is 2 seconds. So that 2 seconds, it is known as a benchmark for that communication attribute. Okay, communication character or the process. So the benchmark, what we say, is a reference point by which something can be measured. So by having this benchmark, we are going to analyze the efficiency of the system. That is nothing but the throughput of the system. So something can be measured, benchmark can be set of performance criteria that a product is expected to meet. So this is one of the performance criteria where we are trying to meet that benchmark. Okay, there is nothing but the efficiency of the system throughput. Then comes the security. So security deals with the protection of data. and application from. So whatever the attribute we are studying, so these attributes are studied when the system is working, when it is operating, when it is not in the off mode. Means when the mobile phone is on and we are operating that one for communication purpose, then we are going to measure all these parameters and all these attributes. That is throughput. What is the efficiency that the benchmark will be achieved? Then comes the security. So what is the security of the data? So whatever the communication is happening, it is happening between two authorized persons, okay, or authorized users. So the security deals with the protection of data and application from unauthorized disclosure, from unauthorized modification, from unauthorized users. So it is not only with users, it is about all unauthorized conditions which are not authorized. So from them, we have to protect the data. So it may be unauthorized modification or unauthorized disclosure or unauthorized users. We need to, from all these conditions, we need to protect the data. So that is nothing but the security. Then comes safety. So safety deals with the possible damages that can happen to the operators or the public or the environment due to the breakdown of the embedded system. So safety is nothing but what? It is about the it is overcome from the possibility of damages due to breakdown of embedded system. So sometimes if I go for the printer and as an example in the ATM machine itself, so in the ATM machine, because of the system breakdown, the printer, it may damage. So what is the safety of that embedded system? It may damage. Or the use of the keypad by the user. So what is the safety that the damage will not occur with respect to that embedded system, that is inputted component? Or you may go for the card reader. So because of unauthorized cards, once we insert in that card reader of that ATM machine, it may damage the component. It may damage that system. It may break down that system. So what is the safety we have taken while designing that embedded system? So even though any card, unauthorized cards are inserted in the card reader, it should not damage. It should not damage. Okay. So that those things will be kept in the mind as an operational quality attribute, safety. So safety analysis is a must in a product engineering to evaluate the anticipating damages. Obviously, what I said, we need to consider it. We should not damage the component and determine the best course of action to bring down the consequences of the damages to an acceptable level. Even though we need to overcome from all these safety measures. Okay, we need to take safety measures while designing the embedded system. Then the next one is reliability. It is a measure of how much percentage we can rely upon the proper functioning of the system. As the reliability of this system increases, the chances of failure and non-functioning also reduces. So while designing a embedded system, what is the percentage we can rely upon these functions? That is reliability. So here it is going to give the small calculation part, that is nothing but the mean time between failure and mean time to repair. So here it is going to define two attributes, that is MTBF, that is mean time between failure and mean time to repair. So what is the time it has taken to failure when the system is failed, and what is the time taken to repair it? So those are the terms define the system reliability. So the mean time between failure gives the frequency of failures in hours, weeks, and months. So if I go for the ATM machine card reader, obviously, how many times it is failing to read a card? How many times it is failing to read a card? Means based on number of insert, the reading operation of that card, what is the percentage? How much it is reading? What is the percentage of the reading function? Then, if something is okay, we are observing the failures. It may be in hours, or it may be in weeks, or it may be in months. So this failure happens per hour, per minute, or per week, or per month. So in a month, how many times it is failed? In a week, how many times it is failed? Or in an hour, how many times it is failed? So we are going to have the measure by the term called as mean time between failure. Then comes the repair condition. So specifies how long the system is allowed to be out of order following a failure. Means once I repair that one, once again if it is failing, there is a failure, it is failing. So once again what I am going to do? Once again I am going to repair that one. So what is the how long the system is allowed to be out of order? Okay. That is known as mean time to repair. Then comes the maintainability. The maintainability deals with support and maintenance to the end user or a client in case of technical issues. This is simply an indication of the availability of the product for use. So in any embedded system design, the ideal value for this availability is expressed as based on that reliability, that is the ratio of the mean time between failure divided by the sum of both failure and repair. So how many times it is failed divided by how many times it is failed plus how many times it is repaired. So that ratio is known as maintainability. So these are the 6 operational quality attributes when the system is working. So maintainability is nothing but what? When the system is on mode, not in the off mode. So when it is on, then only we are going to calculate how many times it is failing to process the data and how many times it is repaired. So that ratio is nothing but what? Maintainability. Then if we move towards non-operational quality attributes, when the system it is in the off mode. So what are the non-operational quality attributes we need to take care while designing the embedded system? The testability and debugging ability, evolvability, portability, time to prototype and market, per unit and total cost. So these are the 5 non-operational quality attributes which are to be taken while during design of embedded system. So what is this testability and debugability? So embedded hardware testing ensures that peripherals and the total hardware functions in the desired manner, whereas the firmware testing ensures that the firmware is functioning in the expected way. So while testing that embedded system, while it is in the off mode, it should be support all testing measures. So debugging ability is a means of debugging the product as such for figuring out the probable sources that create unexpected behavior in the total system. So while debugging that one, so whenever we are using that debugging that product, so all the components should be show the behavior. Evolvability, the evaluability for an embedded system, the quality attribute refers that it is the ease with which the embedded product can be modified to take advantage of new technologies. Means when it is in off mode, when we are testing, after testing and debugging. So if we want to upgrade that one, we want to upgrade that firmware or the hardware, then that must be supported by that embedded system. Means I want to replace the OS, operating system, from older to newer. Okay, or I want to replace the chip from older chip to new chip. So then the evaluability tells that it must be supported by that embedded system. Portability, it is measure of system independence. An embedded product is said to be portable if the product is capable of functioning as such in various environments. A standard embedded product should always be flexible and portable one. So we may replace. Okay, we may replace. It must be portable one. Means in the ATM machine, the card reader, it must be portable from one device to another device, and it must be flexible for the operations. So not only the hardware part, in the software part also. So whatever the programs we have written in the C language while designing that software, if in future, if we want to replace that programming language from C to Java, obviously it must be supported by that device. Means instead of a C language program software we are using in the older machines, older embedded system, if I want to replace that C functioning environment to a Java functioning environment, obviously that environment will be supported by this embedded system. So in embedded product, the term porting represents the migration of the embedded firmware written for one target processor to a different target processor. Means what I said, it is I want to replace a chip which is designed using C program by a chip designed using embedded C or Java. Okay, so those things must be migrated. So that is nothing but what? Porting, what we say. Then comes it is a time to prototype and time to market. It is also in the off mode. When the system it is in the off mode, we are calculating, we are taking the measure of this non-operational quality attribute. That is time to prototype. Time to prototype is nothing but the idea. Yes, I got the idea. What I said, I want to design one washing machine. Okay, now you got the idea. So what is the time to make it or bring it to the lab? When, okay, idea is there in your brain. When you are going to bring it to the lab, so that the beginning process should happen. The beginning, the working of that embedded system should start. Idea is there in the brain. When you are going to convert that brain idea into reality, nothing but bringing that one into lab. So that is nothing but what? Time to prototype. So what is that time to market? Okay, you got the idea and you have designed that one. So time to prototype is nothing but bringing that idea into lab. Okay, on the workbench. On the workbench, on the table in the lab. Then comes the time to market. Okay, when the system is ready. Okay, the first model is ready. When it should be marketed. When you are going to bring that one to the market, from lab to usage market. So those periods are considered, those activities are considered as time to prototype and time to market. So time to market is the time elapsed between the conceptualization of the product and the time at which the product is ready for the selling. Okay, for commercial product or the use for non-commercial products. The prototype is an informal kind of rapid product development in which the important features of the product under consideration are developed. So the time to prototype is also another critical factor. If the prototype is developed faster, the actual estimated development time can be brought down significantly. Means as we work immediately on that prototype, on that idea, obviously we can reduce the time to develop that one. Okay, so we can, with a faster manner, we can develop it. Means we can ready with all the ideas. Okay, so if I have thinking about a washing machine or a printer, let me go for the printer. So obviously, what are the things to be done? How I need to design that embedded system, that is printer. So what are the inputs? What are the outputs? What is the controlling unit? So how many components are used? What are the quality of those components? By considering all attributes. Okay, operation, non-operational, and characteristics. Considering all those things, once I got the idea, then when we are going to start that one. So faster is the bringing that idea into lab. So the faster is the development of that embedded system. That is nothing but time to market. Then after designing that idea, having the idea, time to prototype and time to market, then comes what will be the revenue, what will be the cost per unit. So here the fifth non-operational quality attribute. It is the fifth one is per unit cost and revenue. So cost is a factor which is closely monitored by both end users, those who are buying and those who are manufacturing. Both are taking care of this factor, that is cost. So any failure to position the cost of a commercial product at the nominal rate may lead to the failure of the product. So based on the requirement, this is a key factor, cost per unit. Cost per unit, not complete product, per unit. Okay, so per unit, what will be the cost? So if not a significant nominal rate for that product or a unit, it may fail the product in the market. Okay, so the proper market study and cost benefit analysis should be carried out before taking a decision on the per unit cost, because the revenues depend on per unit cost. So what is the benefit? Okay, how much benefit we achieved, the analysis of that benefit, the revenue, this depend on per unit cost of the embedded system. If the system is costly, obviously it is going to fail in the market. It is not like that. If the cost is less, once again, the user may think about the quality of that product. Okay, so the cost is purely the key factor in the design of embedded system. So this one is explained using this graph. The per unit cost and the revenue, the analysis goes like this. So it has a number of steps. So this unit per cost per unit and revenue, this is analyzed based on some steps over the time. So here the graph is illustrating the revenue over the time. So revenue over the time, it is purely depend on cost per unit. So here it is divided into that time period. It is divided into number of periods. The first period is called as product development, where the product is still under development in the lab. It is not yet kept in the market. It is not kept in the market. So there is no unit cost and there is no revenue from that product when it is in the development stage. Okay, from prototype to the time to market. Prototype is there, and you are designing that one. Time to market means when you are going to bring that one to market. That period is nothing but what? Product development. Okay, when the product is developing in the industry, yes, there is no revenue from that. We can't earn from that product because it's still it is in the development. Means we can't put the unit cost at that time. So this embedded system will get this much cost in the market. We can't analyze. Okay, we can't take any decision during the product development. After the development, once we put that one in the market, then we go for the product introduction. Okay, immediately we need to go for what? We are going to introduce that product in the market. Through what? Through advertisement or distributing the product to the end user. Okay, so the product is introduced to the market. So during that time, there is no profit. There is no profit because it is in the introduction stage. Users are knowing that component. Okay, through advertisement. Okay, new model is appearing, arriving in the car. So the car manufacturer, what they are going to do? Once the development is over, they are putting that one. They are introducing that product to the market. So during that one, they are going to mention the unit cost. In the product introduction part time, we are going to introduce the cost per unit. So they are going to mention what is the basic rate, basic price of that or showroom price for that car, the new model of that car. Okay, and it is fixed one. There is no variation in that unit cost. They are not going to reduce. Once the new product is launched, they are not going to immediately thinking about, oh, we need to reduce the price because there is no sale. It is not like that. It will be kept constant during that product introduction. Obviously, during that one, the sale is less, and profit is also less. You can observe in the graph. Graph. Okay. So cost is constant. The manufacturer or the designer won't disturb this per unit cost. It will be kept constant. Okay. Then what about the sale? So in the product, it is just the beginning of the sale. So if the industry, the car manufacturer industry, introduced a new model car, obviously the sale of that car is slowly increases, and profit is also slowly increases. What you are going to observe on the screen in the graph. Then growth, what we are going to observe, where the maximum sales are going to be happening. There is an increase in the sales. Obviously, the profit will be more. And what about the unit cost? Then the manufacturer is going to decide about based on the revenue. Based on the revenue he is receiving, he is going to reduce or increase the unit cost. If obviously the revenue is more or the product sales are more, the manufacturer is going to think about decrease the unit cost so that he is going to attract more number of users to buy that product. Okay, so in the graph you are going to observe the slowly unit cost is decreased as there is a growth in the product sale, and obviously there is a growth in the profit also, and it is a specific time period. It is not like that it is going as on. Okay, but the growth is going to have its own time period. After that, the product has got its maturity. The peak of sales, it will come and arrive. Okay, after that, there is no more sales of that new model car. Okay, so what about manufacturer? Obviously, once we got that product maturity, he is going to think about another new model, and he is going to stop that older model. He's going to stop that manufacturing of that older model, and he's going to think about a new prototype. So that will be achieved during the period of product maturity, where he got the maximum revenue, maximum profit. He got maximum profit, maximum revenue, and maximum sale, and unit cost is also reduced. It is go on reducing based on the revenue as it is going to increase. Then comes the period is called as product retirement. Obviously, we are going to observe the yearly in the car manufacturing. Yearly, we are going to observe what the product retirement is going to happen. So yearly, they are bringing new vehicles, new models. This is because of what? Studying the market, analyzing these factors, these attributes. So this is illustrated in the graph. Product retirement, where we are going to observe less revenue, less profit, and less number of sales, as well as the unit cost is also decreased. Okay, so at the beginning, the car, if it is sold for 10 lakh rupees, at the retirement time, it is sold for up to lesser than that 10 lakh. Okay, we may observe that one up to 6 lakh or 8 lakhs. Means there is a reduction in the cost per unit. So this is the analysis or the introduction of these operational and non-operational quality attributes, as well as the characteristics of an embedded system. So this is today's session. In the next class, we deal with the application and domain specifications. So how we need to concentrate on designing embedded system based on application oriented and domain specification related issues.